license?
Hello everyone. Arvin. Hi, welcome to Quantum Computing Club. Before we start, I just want to let everyone know we're recording this and it's going to be posted on our website. So if anyone has any concerns or comments, just let me know at the meeting. So let's start. See if this, is there a pen? Can you just go on the laptop? So we're going to start by seeing where quantum computing really came from. So this is a picture of the 1945 ENIAC. And this thing was huge. This was the first general purpose computer that was actually, first general purpose computer built. And it filled a room 30 feet by 50 feet, which is nearly the size of this room. And it weighed over 30 tons, which is ridiculous. And it had 19,000 vacuum tubes, which is what they actually use as bits. Then 40 years later, we get the Apple Macintosh, which looks a lot better, right? And its chip was like half an inch by half an inch. Compare that to the previous computer. In 40 years, we went from 19,000 vacuum tubes, which are these like giant light bulb kind of things, to these little transistors. We got 68,000 of them. Each transistor was 5 micrometers thick, so that's really, really small compared to the vacuum tubes. Now, 40 years later, we get the iPhone 14, and the chip is 14 nanometers by 14 nanometers. For reference, an atom is roughly half a nanometer. So we're pretty close. And we get 16 billion transistors. So we went from 68,000 to 16 billion in 40 years. And again, that's 200,000 more times transistors, and roughly 2 times 10 to the 10 times less space than the ENIAC. So we can actually see the progress that we've made. So this seems pretty straightforward, but what's actually the pattern? So we're getting more transistors and we're getting less space. So actually there's a law that defines this. It's called Moore's Law, and Gordon Moore, which is the guy up there, who was the CEO of Intel, he said that every 2 years the number of transistors double. So if we actually think back at those numbers, they're not just increasing, like 5,000 every year or something. No, they're actually going exponentially. It went from like into the thousands to the billions. Like that's ridiculous in 40 years. And if we just look at these graphs, we can see that the ENIAC and the Apple computer all line up in this same trajectory that Moore's Law has established. Now, the problem with this, it seems really good, right? We're getting technology that's increasing rapidly, and it seems like our future of technology is going to be so good, but once we get so small, those transistors end up behaving in a completely different set of laws of physics. That's what we call quantum physics. And really, quantum physics may sound super complicated, but really all it is, it's just a way of describing the behavior of really, really tiny things. And what happens with this is we get a lot of these strange behaviors like superposition, entanglement, and interference, which actually used to trouble us, but now we harness them for quantum computing. Now, we use these things, and we use them for getting information to be stored in a way that we can't just do that with our normal computers. And then because we have so much information stored, we can just do things that our normal computers can't even get close to doing.
Yep. All right, so what are the applications of quantum computing?
It can be used in many different fields, including drug discovery and personalized medication, because you can show molecular structures with quantum computing. Also, cryptography, you can send securely encrypted messages using quantum key distribution, as well as enhancing artificial intelligence, speeds, and accuracy. Also, you can precisely predict weather events, which can keep people safer from natural disasters, and optimize travel times, because you can test all the possible routes very fast, so you can find the best one. Why should you learn quantum computing? It's a field that will only keep growing and being applicable in more and more other fields. Also, it's fascinating and connects physics, computer science, math, and chemistry. By learning quantum computing, you're setting yourself up for an exciting career. What are some career opportunities? These include quantum researcher, quantum software engineer, quantum algorithm designer, and a quantum error correction researcher.
And actually, we're going to be getting a couple of these to, like, a quantum algorithm designer to come speak to us later, and we'll talk about that in a bit.
And these are just a few possibilities because the field's only growing more and more.
So this year, we're going to be doing a few things. Mainly, we're going to be learning about the properties of quantum computers, what they can do, what's like even their purpose, right? And remember those few things I talked about before? We're going to learn about them: superposition, entanglement, and interference. Those are just a few, but there are much more we're going to learn over time. And like I said, we're going to listen to a few guest speakers come and talk. We're going to have, actually our next meeting, we're going to have Dr. Mark Jackson, which is a representative from Quantum, a decently sized company who's working actually with Ford currently to make quantum sensors for the cars, and which also help automate self-driving vehicles, etc. And we're also going to have Dr. Gorjan Alegic, which is a professor from UMD, and he's actually going to be talking about quantum algorithms with us. So that's going to also be very exciting. And we have a lot more on our way, actually. We're going to planning on getting a speaker for a variety of things, but namely string theory, which connects quantum physics and classical physics, which is kind of interesting. And we're going to do some projects together just so like we can understand the concepts more. So actually up here is a quantum random number generator using lasers, and this is actually a beam splitter. I don't know if you guys have seen that before, but it uses photons and you get a pure random number generator rather than, believe it or not, the random numbers that you get online, not actually random, but this actually is. And we're also going to be doing some quantum circuits, which are going to use the properties over here, using the qubit, which we're going to learn about in a bit. And we're going to do a little bit of an introduction to quantum chemistry, which will be pretty light. And we're also going to demonstrate the double slit experiment, which is like one of my favorite things to do. It's super easy. If you guys are interested, we can actually look at the end of the meeting today. And yeah, thanks for coming. This was just an introduction, but we're gonna get into it. We're gonna get right into it next meeting with our guest speaker on October 4th from the auditorium. That's actually Dr. Mark Jackson right there with Quantum. And thank you so much. Thanks for coming.